Go ahead and move on to the next speaker. The next speaker will be Lauren Jozwiak, who is a grad student at Brown University, and she'll be talking about floor-fractured craters, predictions of gravity anomalies, and observations from Grail.
Hello, are we on and good?
Yep, I can hear you loud and clear.
Okay, well, first of all, I'd like to thank the collaboration of the Grail team who's helped make this research possible. And okay, here we go. So first of all, what are floor fracture craters for people who don't happen to think about them on a daily basis? They are anomalously shallow craters with fractured floors. And within this, there are numerous other morphologies that can help define subclasses, including the types of floor fractures displayed, pyroclastic deposits, venting, patches of marine material, etc. And over time, there have been two postulated formation mechanisms: viscous relaxation and magmatic intrusion in sill formation. And morphology and morphometry studies have shown that magmatic intrusion in sill formation is really the more likely formation mechanism for these craters. And two of the leading reasons for this are both the extent of the shallowing of the crater, which would have required very, very high thermal gradients to shallow the crater, almost unreasonably high. And then also the fact that much of the crater uplift and the floor is non-axis symmetric and indeed shows preference to different parts of the crater floor. And this non-axis symmetric uplift will come into play later, so just hold that in your mind. So some examples of floor fracture craters here. We have the crater Vitello, which has these really beautiful concentric fractures around the uplifted central region. We move on to the crater Descendi. You can see visually it's a very, very shallow crater and has a network of fractures across the floor and some mare infill here. And then also the large crater Humboldt. It has a net of polygonal fractures across the floor and these deposits of mare material along the edges of the crater floor, covering up some of the concentric fractures. So this leads to the question, what can gravity help us to determine about floor fracture craters? So I said the most likely formation mechanism is magmatic intrusion and sill formation. There's a schematic of this shown on the right, and I'd add that this is not to scale, but it is emphasized to show the process here, wherein a dike propagates possibly from the mantle to the base of the crater. It encounters a density barrier in the brecciated region beneath the crater floor. It stalls, it forms a sill, and then the uplifted sill forms either a laccolith or a very, very thick sill, which deforms the crater floor and leads to all of the observed surface morphologies associated with floor fracture craters. So with this in mind, we now have potentially a high-density intrusion beneath the crater floor, which would be observable in the crater's Bugay anomaly. So hence the idea to use Grail to identify the presence or absence of this signal and help to further constrain the formation of these craters. So for the overall Grail analysis, we used the Goddard 720 Bugay solution and categorized three broad categories for the observed Bugay anomaly for these craters. The first is mass-con dominated, and what I mean by this is that the crater is located either within a large lunar basin or at the edge of a large lunar basin, and its Bugay anomaly was indistinguishable from the mass-con associated with the large lunar basin. And thus they were not considered for further studies. The second core category is what we call a null signal, and this is a crater which did not display a distinct Bugay anomaly. And these are predominantly smaller craters with a diameter less than 30 kilometers. And when I say it did not display a distinct Bugay anomaly, I mean that with the absence of, say, an L-rock whack imagery on top of it, you would be unable to distinguish where the crater is in the gravity data. This is contrasted with the third category, the positive center category. And this is a category in which all craters displayed a positive Bugay anomaly within the crater floor region. Now, this anomaly could either be circular, covering the entirety of the crater floor region or simply a positive region within the crater floor. But the broad overarching category is that it was a positive anomaly distinct to the crater and could be used to identify the crater. This is for larger craters with diameter greater than 30 kilometers. So of the floor fracture craters that were not MassCon dominated, 80% displayed positive Bugay anomaly, and 20% displayed what we call the null signal anomaly. And so now we move farther to actually start to tie the Bugay anomaly with the crater morphology. Using a spherical harmonic expansion of 50 to 540, we examined the Bugay anomaly with respect to crater morphology. And what we were looking for were correlations between peak intensity of the Bugay anomaly and surface manifestation of morphologies associated with the intrusion hypothesis. And these can be the floor fractures, especially concentric fractures, pyroclastic deposits, and topographically uplifted regions of the crater floor. So here we have the crater Patavious. I'll note that it is a large crater with diameter of 173 kilometers, and that recent studies by Newman and Baker et al. Have shown that for craters with diameter greater than 150 kilometers, you start to get gravity contributions from uplifted mantle plugs, and as such, there is almost definitely a contribution in this crater, which is contributing to this central Bugay anomaly that you see on the crater floor. Next, we move on to the crater Balaboa, diameter 59 kilometers. And you can see in the Bugay anomaly map at the top, there is a peak in Bugay intensity in the crater floor, especially located in the northeast quadrant. And in the Lola topography with an Alphonus imagery overlain on it, you can see this corresponds very nicely to a series of fractures in the northeast part of the crater floor. And then also down here in the bottom quadrant, we have the radial Bugay anomaly overlain with radial Lola topography. You can see, again, high Bugay anomaly in the center of the crater, falling off as you move away from the crater floor. And we have the crater Vitello again. And see here, this beautiful high Bugay anomaly correlated very strongly with this domed, centrally uplifted region of the crater floor. It shows again in the topography. And I'd like to point out also that this is a much smaller crater of 44-kilometer diameter. So this relationship is holding even as we move away from any possible contribution from an uplifted mantle plug. And we have the crater Repsol and also the associated superposed crater Repsol G, both of which are floor fracture craters. You can see here the positive Bugay anomaly on the floor, and if you allow me a little bit of interpretation, the anomaly appears to be almost circular, and where the circularity of it ends corresponds very nicely to a set of concentric fractures on the northern and northeastern edge of the crater floor of Repsol, perhaps marking the edge of the uplifted part of the crater floor. I'll also note you can see in the Bugay map a very high anomaly to the southwest of the crater, and that corresponds nicely to the floor fracture crater Galvani, which is not shown in this, but is in fact located in this region. And then finally, sort of a coup de grace is the crater Alphonus, which shows just an absolutely gorgeous anomaly here in the northern and northeastern parts of the crater floor, which corresponds to a set of concentric fractures and pyroclastic deposits on the same side, the northeastern floor region. This is also a topographically uplifted region relative to the western part of the crater floor. And this can also be seen in the topography versus Bugay anomaly, where the Bugay anomaly is in fact offset from the center of the crater and is localized in this northeastern region. We also wanted to attempt to model what is going on in this situation, so we used a very simplified model of two plates, a plate for the melt breccia region and then a place for the intrusion. And we derive the dimensions of these from LOLA data, modeling the depth of the crater floor versus the depth of an unmodified crater of the same diameter. And then the uplifted thickness was calculated from flexural models of Witzmann and Schultz. And our models actually at this point are exact order of magnitude approximations of the Bugay anomaly, although especially in larger craters, they tend to overestimate the Bugay anomaly. And this could be due to any number of reasons, as gravity is very complicated in this region for this sort of modeling, but porosity, regional crater density, proximity to other floor fracture craters, and accuracy of the floor flexural thickness models could all play an effect in this slight overestimation. But all this being said, we now find ourselves with the conclusions that Grail observations have shown positive Bugay anomalies associated with floor fracture craters, which implies both a high-density contribution beneath the crater and is supportive of the magmatic intrusion and spill formation hypothesis. Also noted that there are correlations between the locations of positive Bugay anomalies and surface morphologies associated with the intrusion process, further strengthening this observation. We'd also like to acknowledge the NASA Grail Participating Scientist Program grant to J.W. Head, and especially like to thank Roger Phillips for his guidance in this data analysis. And it is part of a larger effort in preparation on the mechanics of floor fracture crater formation. And so with that, I'd like to thank you and take questions.
Great, thank you very much. And if anyone has questions, please go ahead and type them in the presenter questions window. Lauren, I was curious, you were talking about the Alphonsus impact crater, and you mentioned pyroclastic deposits in, I believe, the northeastern quadrant there. And I was curious if you were suggesting that those pyroclastic deposits were associated with the sill formation, potentially a surface rupture of a dike of some sort. Could you comment on that?
Yes, actually, we think they are volcanic eruptions associated with this sill, and as these sill forms and degasses, you'll get periodic volcanic eruptions manifest in these pyroclastic deposits, and they're evident in Alphonsus and several other floor fracture craters as well.
Oh, fantastic. I don't see any other questions coming in at this moment, but if we do have further questions,